Hello, today I'd like to show you my code from a graduate course called Biomedical Signals. The goal of this code was to reconstruct a signal based on Fourier Transform. It uses the generalized Fourier Transform, and that I can show you what the ultimate goal of this code was to reconstruct the signal like you see here. At first you see there's just a red line like when you're trying to make a square wave where the sine wave will make a general representation of this oscillating step square wave or square function, and then it will incrementally add finer and finer detail to these corners. And if that's done infinitely many times, then it can reconstruct the square wave itself. In order to do this, it uses the generalized Fourier series, and that is some function can be reconstructed or constructed from three separate components: a naught, a of n, and b of n. And I can show you the code right now on Matlab. So this code starts out, it lets you choose from four different options. You can choose to reconstruct a step, a ramp, a sinusoid, or an exponential function. So in order to do this, I just did a switch case. So for the step function, or the step case, the user can input the height of the step, the width of the step, and the period of the step. So that would be the difference between the steps from when the step starts all over again. This code is about 800 lines long, and it doesn't need to be that long. I could have done this in about 400 lines, but in hindsight, I had each of these different functions go through a different set for various reasons. One of the things that we had to do with this was define some epsilon, so the error compared to the original function, and then if the error got so close to the original function, it would just stop. So here's the ramp case. The ramp is just some line, and then on the line you have, on the one side of the line, the high side of the line, you'd have some vertical line coming down, and it would represent a ramp, or a sawtooth, if you will. Same with the sinusoid. You could choose between a sine and a cosine, and you can choose between degrees and radians. Here you can see the amplitude would get put in that particular format so that you can see exactly what the amplitude is. And I skipped the exponential. There's the exponential case. Likewise, you'd put in some exponential in this particular form. It's not very pretty. You can, if you don't put it in this way, it will come up with an error. So it's not foolproof by any means. And I had to pad the array just depending on how long the period was going to be. There has to be some zero space in between if you're going to make some period to this function to where it repeats all over again, and then it gives the illusion that it's repeating, but really it's just a replicate of itself moved over however many spaces. And I'll show you that once we get the code started. I give the option to flip the function horizontally along the vertical axis, and likewise I give the option to reflect the function, and as well you can transfer the function horizontally and vertically, like if you wanted to put a DC offset or some sort of time offset. This is, so in my window, the final window that comes up, there will be three different graphs that come up in that window. The first one would be the original function. The middle window will be the nth function, which is the current Fourier sinusoid, and the last function is, or excuse me, the last window is the function that is being constructed in real time. So here you can see A0 is being defined, A naught, as well as A sub n and B sub n for each iterative pass of this while loop. This while loop would be for the square wave case. And likewise, it's going to go through a while loop for the ramp case. I know this is an if, but there's the while loop for the ramp case. And the same thing is going to happen for the sinusoid case and the exponential case. I have for the exponential E being defined as 80%, so it has to be 80% complete for that particular loop to stop. 75% for the sinusoid case. 75% for the ramp case, and 60% for the square wave case. So if we run our function here, and I'll just go with a step. For the width, I'll put in 3. For the height, I want it to be 4. I'm going to put in the period of the function, and that can be 5. So it has a width of 3. It's going to have downtime of 2, so 2 units in between each square wave. I don't want to horizontally shift or vertically offset the function, but I could, I guess, if I wanted. And I could flip it across the amplitude, flip it horizontally along the axis, and vertically, but I'm not going to do either of those. And we'll see it go up in real time. So here's the original function, here's the nth term, and then this is the sum series being constructed. You can see it gets a little bit close here. I have the percent matching in real time. Now the real time will go up and down because as you get closer and further apart, you see here, for instance, you'll get these lines where it's not anywhere near the midline, but then sometimes it'll be very close to the midline. It's at 28% matching right now. I believe it goes up to 30% or 40% in this case and then drops back down. In this particular scenario, it goes to about 20 iterations before it gets past the 60% mark. Getting closer and closer, 58%. Back down to 54. And then it should tell me at the end how many I've done as far as passes. Yep. So the final function, it was actually 32, not 20 iterations of n. We can repeat this whole series again. We're going to try with the ramp this time. But real quickly, before we do the ramp example, I just want to show real quick how the E or epsilon or error that I have is actually defined. When I first ran this problem, I had E for the ramp situation made to 70%, and I found that in this example it just reached the max number of iterations, which was 70, and I wanted it to stop via the error. So I have E defined using the numel function, and this function just counts how many numbers are in a particular array. And so I have this counting the number of times FTT, which is the original function that I make, equal amplitude 4, which is the constructed function that I'm building with the Fourier transform out to 1 decimal place. And then I'm dividing that by the length of amplitude 4. So it's essentially just a ratio. And I can show you that here. The Numa function is 185, I believe. Yes, and the total error in this situation then, in this next example, is 46%. So I've set this to stop at 46%, and I'll show you now. So we're going to run the ramp. I've set the width for this example at 2 and the amplitude at 3 with a positive slope, and the period is 4, and I'm not going to shift it. I'm not going to offset it or reflect it, and it will come up here in a minute. So you can see originally it starts up, it makes that nice curve right at the top to represent it initially, and then you have constructive and deconstructive waves of the sinusoid that build up to make this nice crisp corner here. And as it gets closer, we're at 36%, it'll start to look more and more like the original signal. It's going to get closer here, maybe 1 or 2 more iterations. And the bouncing back and forth, especially the ringing right next to that drop off, is where the real problem is with the error. So close. There we are. And we reached 42 iterations, max was 70 that we could have done. Not a bad deal. I could have set it to 45 and it would have dropped off a little bit sooner, but that's okay. So this is the final version. If we did this infinitely many times, we would certainly get this nice, clean, crisp line, but that's alright. I appreciate you watching my video. Thank you so much. And I hope that you can enjoy some more videos later. Thank you.